Okay, so let's go and fill in our observed. What did we observe? We observed 62 until deaths, 23 homicides, and 5 suicides. If you add those up, you get 90. So for these ones, this is going to be 74% of 90. This one will be 16% of 90. This one will be 10% of 90. So you're going to get, well, this is 9. What's this one here? 66.6 and 14.4? Is that right? Yeah. Okay, good. So then step 1, H naught is O sub I equals E sub I. H1 is O sub I is not equal to E sub I. And then step 2, critical value. Let's see, alpha's 0.10 and your degrees of freedom is 2. What did you guys get? What did you get for critical value?
4.605.
Wait, because you did 90 minus 1. You did 3 minus 1. Because there's 3 categories. 9, 1. Okay. Yeah, minus 1. Yeah, that's weird.
4.605. And then you guys did your chi-squared, which is going to be 62 minus 66.6 squared over 66.6 plus 23 minus 14.4 squared over 14.4 plus 5 minus 9 squared over 9. And what did you guys get for your chi-squared?
7.23.
Great. So somewhere out here?
Yes.
Are you going to reject H naught?
Yes.
Yes.
It has been rejected.
Reject H naught. So enough evidence to reject the claim.
Observed percentages are
That the percentages are as expected. The problem with saying are equal is, again, it's weird because we're not saying that they're equal to each other, and that's what it sounds like you're saying. Right? Yeah?
Didn't you say equal to the research?
Yeah, you can do that. You can say equal to the researchers. You can do that. Totally. All right, so now we need to jump into 11.2.
He said something like, we can't say it because...
Jimmy, go ahead and read.
A test of independence tests the null hypothesis that in a contingency table, the row and column variables are independent.
Homogeneity.
Homogeneity of proportion test is used when samples are selected from several different populations to see whether the proportions of each characteristic are the same between populations. Again, to be clear, we are not talking about cause and effect, merely association, just like correlation.
Right, we're not saying that one causes the other one, we're saying that they're related. They're correlated in some way. They're related. X.
A contingency table or a two-way frequency table is a table in which frequencies correspond to two variables. One variable is used to categorize rows, and the second variable is used to categorize columns. Contingency tables have at least 2 rows and at least 2 columns.
Right, so where we've seen this before is with our puppies, right? We had male and female puppies, at least 2 rows of data, and we had black labs, chocolate labs, and yellow labs. We had 3 columns, so at least 2 columns. That's a contingency table. Here's another example. Here's a visual of a contingency table. Right, so here you have different types of treatment that people could have had, and then whether they're a success or a failure. So rows, columns, and Daniel, thanks for volunteering. Go ahead. Dan,
Remember,
yeah, Daniel?
yeah.
Yeah.
Remember back in chapter
Read the
4,
top part too.
okay, independence of
And homogeneity?
homogeneity of proportions are the same thing. Remember back in chapter 4, if two characteristics are independent, the proportion for one given the other were the same as for the whole proportion.
For population.
Whole.
Okay, independent or dependent. So you guys remember when we figured out something was independent or dependent? We looked at their ratios, the ratio of this versus that compared to this versus that. Everybody remember that? That was how we figured out if things were, we're looking at this ratio. If chocolate and male were independent or dependent, we look at these ratios and see if they're the same or not. This is the same thing. Independence. So instead, what we're looking at is we're looking at not just one of them, but all the proportions. So is this the same as that? And is that the same as this? And is that the same as that? So is 5/8 the same as 15/24, the same as 10/16, the same as 30/48, and they are. Right? So here, the proportions are homogeneous, the same, and they're also independent. Make sense? Right? Because if the proportions are the same, they're independent. So it's the same thing. The test of to test that these proportions are the same is the same as a test to saying that these things are independent of each other. Make sense? Because that's how I figure out if things are independent. Now remember that it's a sample, so it's not going to be perfect. It's going to vary a little bit, right? So we have to remember that okay, it's not going to be perfect. It's going to vary some, because if I flip a coin 20 times, I'm probably not going to get exactly 10 heads. Right? It's going to vary a little bit, just because that's how randomness in life works. But the thing is it going to be close enough? If I get 18 heads out of 20, then that's not really close enough to 10, right? You got to kind of figure out, you know, how close these are. That's where we're going to use these tests. Did you have a question? What was your question?
Can't you just compare the 5 and 3 instead of, have to do 5, compare 5 and 3?
Well, the thing about it, we're going to compare all of them. 5 to 5.
You could compare 30 to 18 and then compare 5 to 3 and like 15 to 9.
Right. So in the case where we're actually going to compare all of them to all of them, kind of in a way. It's going to be a little more. I'm just giving you a simplified version of the idea of it. But yeah, we also could compare other pieces like that. Yeah. Yeah, and then we're going to compare kind of all of them in a sense to all of them and see how far they are apart from each other. So just a couple of ideas about the notation. The O's and E's you're familiar with. R represents the number of rows that you have in the table. Of data, not including your labels, just of the data. Not including your totals either, just the actual data. Not including the totals or the labels. And C represents the number of columns. So in other words, how many items in that category, each of those categories. So like here, male, female, 2 rows. Chocolate, black, yellow, 3 columns. Except you don't count the totals or the labels. Does that make sense to people? 1, 2, 3 columns, 2 rows.
Okay.
Okay. The test. So for this test, H0, you could just use your regular O sub I equals E sub I. You could also use that each proportion is equal. The first proportion equals the second proportion equals the third proportion, and so on for however many proportions you have. For the H1, you can use the generic one, O sub I is not equal to E sub I, or you can say at least one differs. Either one of those. If you reject the null hypothesis, that means there is some relationship. So here, the null hypothesis means no relationship in this case. And then H1 would be is a relationship. Good? So again, my null is always going to be no something, in this case, no relationship. I don't know if that's the same. Couple of things to note here. We are going to have to compute all the expected frequencies. Your calculator compute them for you, but you need to compute 2 of them by hand. The first one and the last one. Okay, so I'll make you do those, just the first one and the last one, not all of them like my first class did 5 years ago. And then, data arranged to make a contingency table. The other thing is the degrees of freedom. Degrees of freedom is your number of rows minus 1, the categories in this group minus 1, times the categories in that group minus 1. So you can have 2 variables going on. Like gender, that's it. Those are how many categories we had. We had male puppies and female puppies. The other thing was type of lab it was. We had 3 categories. We had black labs, chocolate labs, yellow labs. So the number of categories in the first thing minus 1 times another categories in the second thing times minus 1. And you multiply those 2 together to get your degrees of freedom. The calculator will also calculate that for you as well. So that's not that difficult. This is exactly the same. With degrees of freedom, again, being row minus 1 times column minus 1. But the expected frequency you're going to have to use is the sum of the row sum, multiplied by the column sum, divided by the grand total for each different entry you have. We'll go through that in just a few slides. So, stat test for 11.2 and 11.3, it's all going to be calculated. So that part's really easy, very straightforward. We're just going to do stat test, chi-square test. You're going to put your observed values into matrix A, and then you're going to tell it to put the expecteds. It will compute the expecteds for you. Tell it to put it in matrix B, and it will output, it'll take your stuff into matrix A, compute everything, and store it into matrix B for you. They'll also give you your chi-squared value and the p-value. So that's the nice thing. All calculators, including the 83s, have the stat test, chi-squared test. Okay, so the big question is, how do you figure out what your expected values are? This is how you do it. I want the expected value for this guy right here. I'm going to take his row total. This is his row total. You guys see that one over there? I'm going to take his column total. That's his column total. I'm going to multiply those and divide by his grand total. So this one's going to be 119. Oops. 119 times 246 divided by 582. That's the expected value for row 1. So little 1 here, column 1, comma 1. Row 1, column 1. I also need to compute it for this guy here. He is going to be the expected value of what row is he? The third. How many rows are there total here?
3.
3. You guys see ABC? How many columns are there?
3.
3 types of infections. Everybody see that? So ignore the totals and ignore the labels. We're just talking about the actual data. So here's my actual data. Let me show you guys. This is my actual data here. That section there. Janelle moved that over so we can do that. So this is going to be E row. What row is it? 3. What column is it?
3.
3. So it's going to be his row total, 384, multiplied by his column total, 200, divided by the grand total, 582. Good? Very easy to compute. Everybody agree? Totally straightforward, super simple. Everything else is basically, it's the same. Your step 1 is the same, your step 2 is the same, you're just going to have a little slightly different degrees of freedom. You have to compute these 2 things, but then your test stat, you're just going to put that matrix into matrix A, your data into matrix A, and you're going to do your test on it. Steps 4 and 5 are the same. So let me show you how to input it into a matrix, and I'll show you what I'm talking about. Yep. Let me just do that. So, do you have an example on your sheet somewhere? Do you have the hospitals? Do you guys have this?
Yes.
Okay. So let's go ahead and do that. So I'm gonna do second. If I go down to the fourth one, do you see where it says matrix here in blue? I'm gonna hit that one right there, second matrix. And I want A. So I'm gonna go to edit. So scroll to edit, A. How many rows do I have? 3, so I'm gonna put 3 in here. How many columns do I have? 3.
Three.
When I put a 3 in here, see how there's only one column now. When I put a 3 in, all of a sudden it's gonna give me 3 columns.
Ah.
And then it's gonna type it in. 41, enter, it goes across. 27, 51, enter, it jumps down. 36, 3, 40, 169, 106, 109. Done. How easy is that? If you want to change it, you just go up here. If you put the wrong numbers in, you just change this to a 4 or a 2, and it'll change the size of this thing. Then I got to go to stat, test, chi-squared test. So look at this one here where it says chi-squared test. You guys may have GOF test, which is for the previous one, but 83s will just have this one. And I'm going to put my observed in A. It will compute my expected for me and put them in B. Calculate. Super straightforward. My chi-squared is 30.696, so 30.7. My p-value is my p-value 3.53?
No.
Everyone look up. Is my p-value 3.53?
Times 10 to the negative
353%?
No. It's negative
3.53 times 10 to the negative 6.
Yeah. So anytime you have a p greater than 1, you better be looking for an e negative something. So you're going to have to add, this is e negative 6, you're going to have to add 6 zeros to the front of it and then put the decimal place after the first 0. On board? Everybody on board? So then my chi-squared is 30.7. Compare that to your critical value and it all goes the same way as everything else. Okay? Everybody feel all right with that, kind of? We'll go over more of them next class. Have a good weekend.
Well,
Yes.
see more of the